Lesson 1.11, limits to positive or negative infinity. What's different about this lesson is that we can no longer say does not exist for an answer. We're going to have to specifically say whether it's headed towards positive or negative infinity. So those were those functions that have a slant asymptote where the end either goes up or goes down. So you're going to have to say which way is it going? Is it going towards positive infinity or negative infinity, a big number or small number? Okay, I put two graphs up here just to use as a visual for later. You need to know that e to the x, e is about 2.7. It's an irrational number where the digits never stop and they never repeat. It looks very close to the poster on my wall for the parent function of exponential because it's 2 to the x. It's very close. If I have e to the negative x power, having a negative with the x is going to reflect the graph over the y-axis. So you can see how it's this and then flipped over the y. And so it decreases. So over time, what does it do? It approaches 0. I also want you to remember negative exponent rules, where if an exponent's got a negative, you flip it or sink it to the bottom. So I put 1 over e to the x. So it makes sense that as I put in a really, really big number for x, let's say 100, 2.7-ish to the 100th power is going to be huge. And when I take 1 divided by a really, really, really big number, it ends up getting closer to 0 because what you're doing is say, take a pie and you slice into 8 pieces. The pieces are all reasonable size, but if I have one pie and I slice it into 1,000 pieces, you're chopping that bad boy up to where there's hardly anything. It's going to be a mess, right? So the more I take a small number divided by a really big number, I'm making lots and lots and lots of cuts out of that number and making it close to 0. So there's a visual, there's an explanation of why that's going to happen. All right, the first 3 problems are all polynomials. We have no fractions, right? They're not rational, they're just polynomials. And polynomials are continuous everywhere. There's no breaks, jumps, discontinuities, right? So we're trying to figure out what the end is doing. So you could think back to your rules within behavior of polynomials, or what you really need to know is when I plug in a really, really big number, that's what infinity means. The only part that's gonna matter is the part that has the biggest exponent or power. So let's put limit as x goes to infinity of x to the 4th power. When you see infinity, I want you to think that is a really, really big number. So what we're gonna do is plug in literally the word big for x. So that's a really big number, 1,000, 1,000,000, 10 million, and taking it to the 4th power. That's still going to end up being really, really big. So we would say that the end behavior is going to positive infinity. And also you should remember our rules that since this is an even power and it's a positive leading coefficient, both ends would be going up like this. So this is the end we're wanting as x goes to the right. All right, number 2, we have another polynomial. Again, pick out the highest degree power, which is this one. That's the only one that's going to matter. The other things, when I plug in big numbers, this is going to overpower everything else. So we're going to say as x goes to negative infinity this time, I'm going to plug in a negative big number for x. So I know it's weird using words, but it does help your brain visualize this, and this is the way Delta Math will show their examples. All right, so a negative, really, really, really big number. If I take a negative number to the 4th power, what happens? It becomes positive. But it's still a big number to the 4th power. So that would result in an answer of negative infinity. So it's like I'm plugging in the word big, but then in the end, I'm going to replace that big with infinity. I'm just trying to figure out, is it positive or is it negative? So in this example, I would have both ends going down since it's an even power and the leading coefficient's negative. So that makes sense. All right, why don't you pause and try number 3. All right, my work shows that I picked out the highest degree term. That's the only one that's going to matter. Everything else gets overpowered. I'm plugging in negative big for x. When I take a negative to the 5th power, it's still a negative. And then when I take that negative times the negative 6, that becomes a positive 6 big to the 5th. Well, basically what that means is it's going to positive infinity since I got a positive out of this with the leading coefficient. And this follows our rules as well because it's an odd function and it is a negative leading coefficient, that means it's going to end going down, it's going to start going up. So it does something like this. So as we're going to negative infinity, we're going up to infinity. All right, the next two deal with rational functions with square roots. You're going to do the same thing where you pick out the highest degree term on the top and the bottom of the fraction. So in this one, that would be this guy. Bottom, that would be this guy, including the sign. So I'm going to write that again. That limit as x goes to negative infinity of square root of 9. I'm going to plug in negative big. So I can save some room here. That's going to be taken to the 6th power over negative 2 times negative infinity. Dang it. Sorry. I used to teach this, I plugged in infinity, but I found this does work a little better. But I have to fix that habit. Negative big cubed. Okay, so a negative number taken to the 6th power would become positive. So it would be positive square root of 9 big to the 6th over a negative number taken to the 3rd power would be a negative times this negative would become positive 2 big cubed. And then I'm going to simplify my square root. Square root of 9 is 3. 6 divided by that index of 2 is big cubed, and then over 2 big cubed. So here's what's kind of cool is you want to simplify your fraction at the end. So your big cubed divided by big cubed cancels. We actually get a number of 3 halves. And if you graph this, you could see that there's a horizontal asymptote at 1.5 as you go to the left. All right, number 5, let's try another one of these, or if you want to pause, you can. I'm going to pick out the highest powered term on top and bottom. Those overpower everything else. I'm going to plug in a negative big number for x. Okay, a negative number squared would become positive times 4. So I get 4 big squared over, that would become a negative, times 5 would be a negative 5 big cubed. Square root of 4 is 2. Square root of something squared is just too big. Too big. Over negative 5 big cubed. Okay, I want to cancel out a big from top and bottom. So that would make that negative 2/5 over big squared. I need more room. Let's think about this. If you're putting in a really, really, really big number on the bottom, so that's back to saying we have something small divided a whole bunch of times. Each piece is going to get really, really, really small. So the negative in this case doesn't matter. You're going to approach 0. Okay, and if you graphed it, you could see that. So we're approaching 0 because the denominator is so big. Okay, and then we get to just regular old rational functions. Pick the highest term on top and bottom. And then I'm going to plug in big. And nothing's negative, so that doesn't affect anything with the exponents. This is negative 5 big to the 5th over 3 big squared. Take out big squared from the top and the bottom, and I get negative 5 big cubed over 3. Let's think about if you plug in a really, really big number like a million. So you have negative 5 times a million is negative 5 million divided by 3. That's going to still be a really big number, but it's going to be negative. Let me show you on a calculator. Okay, this is actually negative 5 billion divided by 3. You can see that this number is still very, very, very large, but it's going to be a negative because I have a negative divided by a positive. So this will approach negative infinity. Okay, now it's a very abstract concept. Why don't you pause and try number 7? Okay, plug in your negative big. That makes it positive on top, but a negative on the denominator. You cancel out a big from top and bottom. So I end up with something to the third power, a really, really big number. So that's like the example on 6. So it's going to be an infinity, but it'll be negative because I have a negative divided by a positive. And again, graph them after you do them by hand and see if it worked. All right, then we get into things with E. That's where the graphs above might help us. We're going to plug in infinity. Again, figuring out which is going to overpower in the top would be the x squared. So that'd be a big number, squaring it. The 4 is not going to affect it. This E to the negative big number is going to do something for us. Okay, so big number squared is just a big number squared. But what happens when I said we have a negative power? Remember that second graph? That means that it really needs to flip-flop. So if I had E to the negative power down here, to make it positive, it would come up to the top. So it'd be E to the big. So actually I don't have a denominator at all anymore. So if these were big numbers, that'd be big. And 2.7 something to a really big power would be big. Everything's positive, so we would end up going to positive, really, really big, infinity. All right, number 9, we've got cubed and an e to the x. Which did we say grows faster? The e to the x, the exponential one. So this and this are all that matters. So we got a negative of a negative big number. Oh, I put that in the wrong spot. I should have E. I'm sorry. Negative E to the negative big power over 4 times negative big. Okay, so again, this would sink to the bottom, but I would still have a negative on top, so I'll put a negative 1. This would multiply to be a negative 4 times big, and then this times E to the big. Okay, and then we've got, that would be a negative times a positive, and so that's really big on the bottom. So 1 divided by a really big number, even though there's negatives there, would come to 0. All right, done with those. The last 3 are different as well. 10 and 11 have multiplication, so those you have to plug into each piece and see what happens. And then number 12 is just with E. So let's try number 10. We have the 6 really not doing anything, but this negative 4x is important, times e to the negative x. So limit as x goes to infinity of negative 4 times a big number times e to a negative big. And then since this is going to be a negative power, we'll sink it to the denominator. So we got negative 4 big over e to the positive big. Which one overpowers the other? Definitely e to some really big power. So since this is bigger, think about having something small divided by a really big number. We said that approaches 0. Okay, you pause and try number 11. Okay, the only part that matters is 5x cubed. I plugged in negative big. Cubed would get a negative 5 big cubed, and then this is a negative times a negative big number, which makes a positive. So nothing goes to the denominator. This is going to be a really big value. This is really big, so it's an infinity, but it'd be a negative because it's negative 5 times 1. All right, and last one. We've got negative e to the x plus 3 power. Would look like limit as x goes to negative infinity of a negative e to the negative big plus 3. If we have negative 1,000, is adding 3 to it really going to do anything? No. So we really have this. So there's a negative 1 in front. I'm going to keep that in the numerator. Then I'll sink down e to the positive big. So again, when we have a small number divided by something really, really big, that approaches 0.